Most engineers treat the fuel system as a utility. That is the first mistake. A fuel system is not just pumps, headers, filters, valves, and vessels. It is the energy backbone of an industrial plant. It determines whether furnaces remain stable, boilers keep producing steam, turbines continue generating power, emissions remain controlled, flare loads stay manageable, and emergency operation remains possible. If you are a design engineer, automation engineer, process control engineer, AI engineer, manufacturing automation specialist, or engineering manager, you need to treat the fuel system as a combustion stability system, energy balancing system, availability protection layer, emissions control enabler, and increasingly an AI-ready operational intelligence platform. The purpose is not merely to move fuel from storage or process sources to consumers. The real purpose is to convert variable, unstable, sometimes contaminated, and sometimes low-value energy streams into safe, stable, controllable combustion under normal, abnormal, startup, shutdown, maintenance, and emergency conditions. That is where the engineering challenge begins. In refineries, petrochemical complexes, gas plants, power islands, and process-intensive facilities, fuel may include refinery fuel gas, natural gas, syngas, flare gas recovery streams, off-spec LPG, vaporized LPG, recovered low-pressure gas, long residue, short residue, cracked residue, asphaltic material, gas oil, light tops, or heavy fuel oil blends. Each stream has its own pressure, temperature, heating value, Wabi index, viscosity, dew point, contaminant profile, stability behavior, condensation risk, coking tendency, and combustion consequence. So the fuel system must not be designed as a static supply package. It must be designed as a dynamic operating system. The first design principle is availability. If the fuel system feeds critical boilers, fired heaters, gas, steam systems, power generation, or emergency utilities, interruption has cascading effects. Loss of fuel can mean loss of heat, steam, electricity, compression, process stability, flare recovery, safe shutdown support, and restart capability. The first question is simple. Which consumers must continue operating during abnormal, emergency, startup, shutdown, or boxed-in conditions? That answer defines pump sparing, storage capacity, backup fuel strategy, independent drive philosophy, emergency power supply, dual fuel requirements, minimum circulation, instrumentation redundancy, automatic standby cut-in, and automation response. For critical rotating equipment, N+1 or N+2 sparing may be required. Independent drive sources may be needed where one power failure can compromise the whole system. For fuel oil service, a mix of electric and steam turbine drives, independent electrical buses, emergency board supply, and automatic standby pump cut-in may be necessary. For maintainable equipment such as filters, heaters, strainers, exchangers, vessels, and control valves, the design must allow isolation, cleaning, inspection, switching, flushing, draining, and restart without forcing a full fuel system outage. The deeper failure mode is not always equipment failure. Sometimes it is maintenance forcing the energy backbone offline. That is poor design. The second design principle is fuel balancing. In many process plants, fuel is not only consumed, it is also produced. The plant may generate fuel gas, flare recovery gas, off-gas, vent gas, syngas, off-spec LPG, long residue, short residue, cracked residue, or asphaltic streams that must be consumed, recovered, stored, reprocessed, or flared. Good fuel system design reduces flaring, reduces purchase fuel dependency, stabilizes energy consumption, and gives operators controlled flexibility. Dual fuel consumers are strategically important. A boiler or furnace capable of firing both gas and oil can shift the gas-to-oil ratio based on fuel gas header pressure, fuel gas availability, fuel oil inventory, emissions constraints, process demand, and startup requirements. When fuel gas production increases, gas firing can increase. When gas production decreases, oil firing can increase. When gas pressure falls, natural gas or vaporized LPG can support the header. When gas pressure rises, consumers can absorb more gas and reduce flaring. But fuel balancing cannot rely only on manual operation or basic pressure control. Fuel balancing involves gas production rate, gas composition, heating value, Wabi index, header pressure, consumer demand, fuel oil availability, fuel oil viscosity, burner limits, emissions limits, flare system load, LPG vaporizer readiness, natural gas backup response, equipment availability, ambient conditions, and future process unit transitions. A pressure controller reacts. A higher-level fuel management system can anticipate. This is a valid AI use case. Supervisory advisory above conventional control loops, not replacement of safety systems. The third design principle is combustion quality. Fuel is not acceptable merely because it reaches the consumer. It must arrive in a burnable, controllable, stable, and safe condition. For gaseous fuels, this means pressure, temperature, density, calorific value, Wabi index, moisture, contaminants, and liquid-free delivery. For liquid fuels, this means pressure, temperature, viscosity, filtration, compatibility, thermal stability, and atomization quality. Gas turbines require a narrower window: dry gas, clean gas, correct pressure, Wabi index control, adequate superheat above dew point, contaminant control, and limited rate of change in composition. A fuel gas acceptable for refinery furnaces may be unacceptable for gas turbines. Furnace burners may tolerate moderate composition variation with proper air-fuel control. Dry, low-NOx gas turbine combustors may suffer instability, emissions excursions, combustion dynamics, or life reduction. Design must begin from the consumer backward. Start with burner, boiler, furnace, turbine, combustor, atomizer, and control requirements. Then design the fuel system to meet those requirements under every credible case. For gaseous fuel systems, the main risks are header pressure instability, poor mixing, liquid condensation, liquid carryover, sudden calorific value change, incorrect air-fuel compensation, LPG condensation, natural gas expansion cooling, hydrate formation, inert dilution, flare gas variation, and excessive flaring due to poor buffering. A central mixing and knockout vessel is not just a separator, it is a dynamic stability device. It reduces liquid carryover risk, slows composition change, provides hold-up, absorbs pressure swings, and gives the control system time to respond. Where high-pressure gas sources exist, a high-pressure buffer vessel can absorb or release gas during demand swings, reducing flaring during overpressure and reducing makeup fuel during underpressure. But it must be sized against real transients: largest producer trip, largest consumer trip, boiler load swing, flare recovery compressor trip, sudden liquid fuel failure on a dual-fired unit, LPG vaporizer delay, natural gas backup letdown, and startup demand. Fuel gas systems should not only be hydraulically sized, they should be dynamically stress-tested. Dynamic simulation should evaluate producer trips, consumer trips, LPG vaporizer response, natural gas switchover, fuel gas composition steps, gas turbine fuel switching, boiler load swings, flare recovery compressor trips, startup sequences, shutdown sequences, and emergency boxed-in operation. Liquid carryover is one of the most dangerous fuel gas failures. Liquid and fuel gas can cause burner instability, flame out, overfiring, incomplete combustion, pressure pulsation, control valve damage, and gas turbine damage. Liquid may appear due to expansion cooling, water saturation after scrubbing, heavier hydrocarbon condensation, poor heat tracing, inadequate insulation, low point accumulation, compressor aftercooling, improper LPG vaporization, natural gas letdown cooling, ambient temperature change, or inadequate dew point margin. The correction is not only a knockout drum. The better correction is preventing liquid formation through worst-case dew point calculation, gas heating, heat tracing, insulation, avoiding stagnant cold sections, correct low point drainage, and adequate superheat margin. For gas turbines, dry gas with sufficient margin above dew point is essential. AI can add value through real-time dew point risk prediction using gas composition, pressure, temperature, ambient condition, vaporized LPG fraction, butane content, natural gas letdown cooling, and header heat loss. The objective is to warn before condensation becomes liquid carryover. Fuel gas composition is another hidden control variable. Many systems assume density correction is enough for air-fuel ratio compensation. That may fail when inert gases, hydrogen, carbon monoxide, syngas, nitrogen-rich gas, flare gas, or unusual off-gas streams enter the mixture. Density may no longer represent heating value accurately. The result can be wrong air-fuel ratio, excess oxygen, fuel-rich combustion, high CO, high NOx, poor heat release, furnace imbalance, stack losses, and unstable combustion margins. Corrective action may include gas chromatographs, calorimeters, Wabi index analyzers, fast density measurement, predictive composition soft sensors, AI heating value estimation, and integration with combustion controls. Alarms should include rate of change, not only absolute value. A fuel gas can be within limits and still change too fast for the consumer. LPG vaporization is useful for fuel gas support during low fuel gas availability or startup, but vaporized LPG is not automatically safe fuel gas. If butane or heavier hydrocarbons are present and downstream temperature is too low, condensation can occur. The design must evaluate maximum butane and heavier hydrocarbon concentration, calculate dew point, maintain temperature margin, and verify vaporizer transient response. A vaporizer with theoretical capacity but poor readiness is not a reliable backup. Heating coil condensate, poor heating medium control, cold standby condition, inadequate holdup, or poor drainage can make it fail when needed. AI can monitor vaporizer readiness through heating medium condition, condensate drainage, LPG level, pressure, temperature profile, control valve position, heat transfer response, standby losses, and previous response tests. Natural gas backup is cleaner but not risk-free. High-pressure letdown can cause severe cooling, hydrate formation, valve icing, and downstream condensation when mixed with hydrocarbon-rich fuel gas. Corrective design includes preheating, hydrate evaluation, downstream temperature control, dew point margin check, letdown valve design, and monitoring of mixed gas temperature. AI can predict cooling impact before switching and recommend preheat requirements. Flare gas recovery reduces energy waste and emissions, but recovered flare gas can contain inerts, heavier hydrocarbons, water, contaminants, and variable heating value. The goal is not maximum recovery at any cost. The goal is safe recovery without destabilizing combustion. A flare recovery optimizer should consider compressor capacity, flare header pressure, air ingress risk, recovered gas quality, inert content, fuel gas header impact, emissions benefit, and consumer stability. Gas turbine fuel systems demand stronger discipline. Fuel must be dry, clean, correctly pressurized within WABI index limits, within contaminant limits, and stable during transitions. Constant WABI index does not mean identical combustion behavior. Hydrogen-rich gas, syngas, LPG-rich gas, methane-rich gas, and inert-rich gas can behave differently even when heat input appears manageable. The right question is not only, can this gas burn? The right question is, can the turbine live with this gas? A real-time gas turbine fuel advisor can monitor WABI index, heating value, pressure, temperature, dew point, hydrogen fraction, inert dilution, rate of composition change, exhaust temperature spread, combustion dynamics, vibration, and emissions response. It can recommend ramp rates, warn against fast transitions, and detect abnormal combustor behavior. For liquid fuels, especially heavy fuel oil, long residue, short residue, and asphaltic fuels, the central variable is viscosity. The burner does not care what the fuel is called. It cares whether the fuel atomizes. If viscosity is too high, atomization deteriorates. Poor atomization creates large droplets, incomplete combustion, smoke, particulates, flame instability, fouling, coking, and burner problems. Fuel must be heated enough to pump and atomize, but not so much that it cracks, cokes, flashes, fouls, or degrades. The liquid fuel system operates inside a narrow thermal window. Hot enough to pump, hot enough to atomize, not hot enough to destabilize, hot enough at the most remote consumer, stable during low flow, protected against stagnant cooling, trace heated against solidification, flushable before shutdown, and filtered enough to protect burners. Heavy fuel systems are not pump heater filter loops. They are thermal stability systems. Long residue, short residue, and asphalt systems may look similar but have different risk profiles. Long residue typically operates at lower temperatures. Short residue requires higher storage and distribution temperature. Asphalt systems operate at higher temperatures and may generate vapors, sludge, coke, and severe fouling. The heavier the fuel, the more the design is governed by pour point, viscosity temperature behavior, thermal stability, coking tendency, blend compatibility, storage temperature, pump selection, heat tracing reliability, circulation velocity, dead leg minimization, filter cleaning frequency, surge drum design, vent handling, and flushing strategy. Heavy residue is not simply hot oil. It can age, separate, form sludge, generate vapor, foul surfaces, block filters, and expose weak thermal design. Fuel oil storage is part of the fuel system, not just inventory. The tank must preserve pumpability, safety, and fuel quality. Storage temperature must remain above pour point and support flow to pump suction, but overheating can cause water boiling, vapor release, thermal degradation, and unsafe vapor conditions. For heavy and asphaltic fuels, tank design must consider heating coil location, suction elevation, water drainage, blanketing, vent treatment, odor control, fire risk, uniform temperature, mixer requirement, sludge accumulation, overheating prevention, and pump suction viscosity. AI can support storage reliability through tank thermal stratification modeling, viscosity prediction at pump suction, heating coil performance detection, water presence risk, and fuel aging prediction based on residence time and temperature history. Blending is a design risk. Blending residues with diluents or other residues may be necessary for viscosity control or disposal, but incompatible blends can cause asphaltene flocculation, sludge formation, filter plugging, and fouling. Do not assume standard commercial fuel blending correlations apply to unstable residues. Do not use storage tanks as primary mixing vessels. Avoid static mixers where cracked fuels may block passages. Verify compatibility at actual operating temperature. Monitor filter differential pressure as an early warning. Use controlled inline blending or dedicated mixing where required. AI can support predictive compatibility screening using crude origin, residue type, viscosity, asphaltene tendency, blend history, lab results, filter plugging history, and fouling events. Heavy fuel systems depend on circulation. Circulation maintains temperature. Temperature maintains viscosity. Viscosity maintains pumpability, like pumpability maintains combustion. Dead legs, stagnant branches, poorly traced valves, unflushed consumer lines, standby equipment, relief paths, drains, and isolated subloops become blockage points. Corrective design includes short branches, subloop circulation, minimum circulation velocity, heat tracing, insulation, mechanical minimum stops on return control valves, flushing connections, hot standby pump warming, thermal reliefs, proper vent and drain layout, and avoidance of stagnant high-risk pockets. AI thermal network models can predict low-temperature zones, stagnant risk, viscosity increase, and potential blockage before the line becomes unpumpable. Fuel heaters must balance atomization and coking risk. If fuel is underheated, atomization fails. If it is overheated, coking begins. For heavy residue and asphalt, heater design must avoid high film temperature, low velocity, excessive heat flux, hot spots, stagnant pockets, and poor turndown. Steam, heat transfer fluid, electric heaters, and direct-fired heaters all introduce specific failure modes. AI can support heater operation through fouling prediction, film temperature estimation, heat duty monitoring, abnormal heat transfer detection, and coking risk scoring. Filters are not accessories, they are diagnostic sensors. A clogged filter can indicate incompatible blending, sludge, coke, asphalt instability, heater fouling, tank contamination, or upstream process upset. For heavy fuel, filters must be spared, switchable online, drainable, ventable, cleanable, monitored by differential pressure, and safe for operators to maintain. Asphalt systems may require auto-cleaning or back-flushing filters. AI can detect abnormal fouling patterns and correlate them with blend changes, fuel temperature, heater duty, tank age, residue source, and operating history. Asphalt burning systems are among the most demanding fuel systems. The philosophy is direct. Keep it moving, keep it hot, keep it filtered, keep it controlled, and always be able to flush it. Failure consequences include line blockage, coke formation, filter plugging, burner plugging, surge drum sludge, vapor release, pump overload, loss of circulation, personnel exposure, inability to restart, and extended outage. Asphalt systems need surge capacity, vent gas routing, overfill protection, blanketing, tight shutoff valves, heat tracing of vent and relief lines, safe hot liquid relief routing, standby pump hot circulation, subloop flushing, and robust instrumentation. For asphalt systems, AI is not optimization first, it is failure prevention. Low boiling fuels such as light tops, light naphtha, gasoline range material, and off-spec light liquids must remain separate from fuel oil systems. They should not be heated casually. They require fire-safe layout, pressure control, leakage minimization, proper disposal logic, and clear operating procedures. Gas oil may be useful as flushing medium, viscosity diluent, diesel fuel, or gas turbine distillate backup, but it must not be injected casually into high-temperature systems where flashing may occur. Before use as flushing medium, check boiling range, system temperature, pressure, compatibility, and flashing risk. Oil and water emulsions can reduce apparent viscosity of heavy residues, but they introduce emulsion stability, surfactant dependency, water loading, stack plume, burner compatibility, and emissions concerns. The common weakness in many fuel systems is that they are mechanically adequate, but digitally weak. They were designed around static margins, conventional alarms, operator experience, and equipment sparing. But modern plants demand lower emissions, reduced flaring, higher fuel flexibility, higher availability, better efficiency, deeper automation, and fewer shutdowns. The typical weaknesses are predictable: static design for dynamic behavior, poor visibility of fuel quality, reactive maintenance, weak integration between fuel management and combustion control, unproven backup systems, under-instrumented dead legs and thermal risks, and alarms that report final failure instead of developing risk. The correction is equally clear. Use dynamic simulation, measure fuel quality, build soft sensors, instrument failure modes, monitor readiness, model dew point risk, predict viscosity, predict coking, predict filter plugging, predict heat tracing failure, predict vaporizer weakness, predict backup fuel unavailability, integrate fuel controls with combustion controls, energy management, flare minimization, and emissions monitoring. For automation engineers, the job is not only control loop implementation. The job is making the system observable, controllable, diagnosable, and resilient. Ask the hard questions. Do we measure the variables that truly define fuel quality? Can the control system detect composition change fast enough? Are pressure controls coordinated with fuel balancing? Do we know viscosity at the burner or only heater outlet temperature? Are filter differential pressures used diagnostically? Are vaporizer readiness and standby conditions monitored? Are heat tracing failures visible? Can operators see backup fuel readiness clearly? Do alarms detect developing failure or only final failure? Can AI improve early warning without compromising safety logic? Automation must convert fuel system complexity into operating clarity. For AI engineers, fuel systems are strong industrial use cases because they contain nonlinear behavior, interacting variables, incomplete measurements, slow and fast dynamics, degradation, transient operations, safety boundaries, and high-value early warnings. But AI must respect engineering hierarchy. AI must not bypass safety systems, replace relief design, replace burner management, or directly manipulate critical controls without validation. AI should first enhance visibility, prediction, anomaly detection, advisory control, readiness scoring, and operator decision support. The best AI in fuel systems is disciplined, bounded, explainable, and tied to real failure modes. For design engineers, the fuel system must be designed for normal operation, startup, shutdown, producer trips, consumer trips, fuel switching, fuel quality variation, maintenance isolation, flushing, inspection, instrument failure, utility failure, power failure, emissions constraints, emergency operation, and future fuels. The physical design must be robust before the system becomes digitally intelligent. AI cannot compensate for poor layout, missing isolation, undersized vessels, weak heat tracing, inadequate flushing, wrong pump selection, unsafe vent routing, or untested backup systems. Good AI amplifies good engineering. It does not rescue careless engineering. The final design discipline is this: design from the consumer backward. Treat fuel quality as a controlled variable. Validate transients, not only steady state. Build maintainability into the layout. Make heavy fuel systems flushable by design. Instrument the failure modes, not only convenient points. Use AI to predict, diagnose, optimize, warn early, rank risk, recommend action, and validate readiness. Do not use AI as decoration. Do not use it as a substitute for engineering. Do not use it as a dashboard layer above weak fundamentals. A fuel system is not a pipe rack utility. It is the energy nervous system of the industrial plant. When it is designed well, the plant runs quietly. When it is designed poorly, operations, maintenance, management, regulators, and sometimes the surrounding community all see the consequence. The future of fuel system engineering is integrated fuel intelligence, mechanical robustness, process discipline, automation visibility, AI-enhanced prediction, and operator-centered decision support. That is the direction modern industrial design must take, because future plants will not be protected by equipment alone. They will be protected by engineering systems that sense instability early, understand fuel behavior clearly, and respond before small deviations become plant-wide failures.